Good morning and welcome to this webinar on rolling bearing damage and failure analysis, and it's a snapshot. So I want to start off by noting several things. Number one, we are focusing on rolling bearings, so we won't be discussing damage in plain bearings or any other bearing type today. Secondly, this being a snapshot, we will be giving a concise overview, as those of you who might be familiar with this topic know that it is a challenge, and it's impossible to cover it in 30 to 40 minutes in the depth that one would really want to get into it. So thirdly, don't be concerned about capturing everything. As Behzad mentioned, we've put a link in. I'll be honest, most of the information I have here as far as slides and data are in that bearing damage and failure analysis handbook. That's an SKF publication. Okay, so you will have access to that and you can read through it. There's a whole lot more in it. At your leisure, you can go through it. Now, brief introduction, as Behzad mentioned, my name is Devan Devalia, and working as an application engineer with SKF Canada. I work as part of a team that's responsible for supporting the industrial bearing market in Canada. Basically, we cover everything except automotive and aerospace, which within SKF are separate business units. I work out of the Scarborough office, which is the Canadian SKF headquarters. And I currently primarily support SKF customers in Ontario and Manitoba, as I have other colleagues across Canada taking care of other regions. One of my regular support activities as an application engineer at SKF is performing bearing failure analysis. So I do have some practical experience with it, and what's nice about this field or this area is that the more you do it, the better you become. It's all about experience and seeing the damage in various forms and understanding applications, and then drilling down to try to figure out primary causes and root causes. And then figuring out corrective actions out, as a result. I will, like Behzad said, I aim to take questions at the end, as I'm going to try and be, as smooth and efficient as I can be through the presentation. Okay, so let's get to the presentation here. So the quick intro, rolling bearings are critical components in rotating equipment, as we all know. Exacting demands are put on them, load carrying capability, running accuracy, noise levels, frictional losses, life, reliability. So over the years, there has been extensive research into how to improve the performance of rolling bearings. And it's almost developed into a science of its own. SKF has been somewhat of a pioneer in the field. Just a quick, I guess, proof is that those who work with rolling bearings may be aware of the L10 life calculation, and it actually is based on work carried out at SKF in 1947 by Gustaf Lundberg and Arvid Palmgren in Sweden. That formulated the equation, and the equation has since been improved upon. But despite all the improvements and developments in design and manufacturing, we still find that bearings do not live out their expected service life. So premature bearing failure occurs for many reasons, but by examining the evidence that's left behind, we can often identify the cause, which will lead us to the appropriate corrective action. So today we're going to spend some time together, get a snapshot, a quick overview of some of the indicators that signal possible issues with rolling bearings in operation. We'll identify and classify observed bearing damage, and we'll see how each failure mode actually connects directly to a specific corrective action. So just to quickly put things into perspective, every year around the world, an estimated 10 billion bearings are manufactured. And only a small fraction actually fail. Most of them, some 90%, actually outlive the equipment in which they're installed. So, your washing machine, dishwasher, etc. Oftentimes, you're throwing the unit out and the bearings are still functioning, right? A number of them are actually replaced prior to failure for preventive reasons. And approximately 0.5% of the bearings are replaced because they're damaged or fail. And so doing the math, this means about, let's say, 50 million bearings are replaced every year due to damage and failure. There are several reasons why they fail or they're damaged. Generally speaking, we've found about a third fail due to fatigue, a third due to lubrication issues, about 1/6 due to contamination, and another sixth for other reasons such as improper handling, mounting, or maybe loading profiles that were unexpected in the application, and possibly wrong or inadequate fits. How the bearings mounted on the shaft and in a housing. We'll find that the figures actually do vary depending on the industry or the application. In pulp and paper, for example, a major cause of bearing failure is contamination and inadequate lubrication, not necessarily fatigue. I love this slide as an application engineer for a bearing manufacturer. So when we come upon a failure in a piece of rotating equipment and we begin to look at the where, the what, the why, one key piece of forensic evidence is the bearing itself. And we do like to say that the bearing is a victim because the true root cause for the failure is often outside the bearing cavity. Okay, so there's a variety of causes that can lead to bearing damage and ultimately failure. Like we mentioned, some improper installation, inadequate lubrication, etc., etc. And all of these leave distinctive marks or evidence on the bearing components, be it on the raceway, the cage, the rolling elements, the bore, or any of the outer surfaces. So, and the objective is to reduce the incidence of or eliminate the incident of a future failure. Okay. So I just wanted to mention that damage in a bearing is not static. Okay, so I just wanted to introduce this concept of damage progression. It is key when we perform bearing failure analysis for us to understand that damage progresses and worsens over time. And we can understand that in a rolling bearing where we have these rolling elements constantly hammering on the different areas of the bearing, depending on the loading direction and the type of loading, etc. But we know there's these balls or rollers that are moving. And if there's any damage, for example, on this slide, we see in tile A there, where a hard contaminant was overrolled, made an indentation on the inner ring of a cylindrical roller bearing. Well, that spot is getting hammered continually. The faster the bearing is going, the quicker this progresses. In a slower application, it may be contracted. It may, well, let's say lengthened. It might progress a lot slower, but the point is that it will grow. Okay, so we see tile A, like I mentioned, the initial damage. In B, we see as we overrolled over a period of time, we get spalling or flaking behind that indent. And in C, again, until D, where we wouldn't necessarily even be able to identify or determine that this flaking or spalling was caused by an indent. So, catching a damaged bearing, early is key. It is helpful. It gives us a higher likelihood of being able to determine the initial or primary damage, and so come to a root cause. So we can do several things to help us catch bearings early. One could be monitoring vibration levels. We know that machines vibrate, and we can use vibration to detect or determine that there is damage in the bearing early. We can monitor temperature. Bearing temperature is a good indication, especially when it starts to trend up, that something might be going on in there. Um, or even monitoring lubrication conditions. So sampling oil and grease regularly might, give us an idea that there's wear particles from the bearing, and trigger us to say, hey, we need to pull this bearing and have a look at what's going on in there. Okay. So straight into the meat, ISO failure mode classifications. So there are a large number of bearing manufacturers, as we know, and there are many publications on bearing damage and failure. And these different publications classify bearing damage and failure in different ways, and may use differing terminology. So back in 1995, a work group was formed, and believes, a lot of the major bearing manufacturers were involved, including SKF, to define a common classification method and terminology for different types of rolling bearing damage. So ISO standard 152, so I would say 15243, was published in 2004 and updated in 2017 as a result of that work. Okay. The work group established that a cause for failure shows a certain characteristic, that a certain failure mechanism can be associated with a certain failure mode, and thirdly, that from the damage observed, one can, well, try to, but one can define the root cause of the failure. Now, I understand, I'm always nervous when folks use the phrase root cause, because in a true RCFA, root cause analysis, let's say, the true root cause may not be in the machine. It would have an human element. So let's just say root cause, let's say closest to the bearing for failure. But if we really, performed an RCA or RCFA, we would often find that the true root cause is something outside of the machine. Okay, but at least it would help us move in that direction. Now, as far as the failure modes themselves, just to note that SKF, when we do perform bearing failure analyses, we actually use these classification, proper terminology as part of our language in the reports we generate. But this is the overview, and it is made up of 6 main modes with sub-modes underneath those modes. And altogether, there's roughly 14. There's 14 failure modes in total. And just a quick note that ISO 15243 does not cover manufacturing defects, design problems, etc. So these modes are in effect as soon as a bearing leaves the factory. So as soon as a bearing is packaged and leaves the factory, it is considered to be in service. So any damage incurred thereafter would fall and be able to be categorized or classified under one of these failure modes. So we have subsurface initiated fatigue and surface initiated fatigue under the fatigue mode or class. Under wear, we have what's called abrasive wear and adhesive wear. Under corrosion, we have moisture corrosion, and we have under frictional corrosion, we have fretting corrosion and false Brinelling. Under electrical erosion, we have excessive current erosion, current leakage erosion. We have overload deformation and indentations from particles under plastic deformation, and we have under cracking and fracture something called forced fracture, fatigue fracture, and thermal cracking. So in the slides that are coming up, we're going to dive a little deeper, not too deep, and I apologize in advance for the condensed slides that give an overview. But as I mentioned, with that PDF that you'll get your hands on, you'll have some time to digest and chew on what we're going to discuss. Okay, so let's dive into fatigue. So under the fatigue, the general definition is basically a weakening, a change in the metallurgical structure of a raceway contact and or the rolling element surfaces in a bearing, caused by accumulation of stresses or material imperfections, finally leading to spalling or flaking of the surfaces. So here's the heavy slide. So in a rotating bearing, cyclic stresses and changes occur, okay, beneath the contact surfaces of the raceways and rolling elements. So if we look at a rotating inner ring on a radial bearing, so the load's going perpendicular to the shaft through the bearing, and let's consider it, being a horizontal shaft, let's say. If we looked at one particular point on the ring as it rotates, we would understand that one point rotates or enters through what we call the load zone or the loaded area of the bearing and reaches a point of maximum load or stress before it exits and then comes back around. So with each revolution, this point on the raceway is entering and exiting that load zone. And below the load zone, a few micron below the raceway surface is where we have maximum stress, okay? So right here, and the stress is compressive and shear. Okay, so we have shear stresses and compressive stresses occurring there cyclically. So over time, the metal gets worked, gets mechanically worked. So depending on the load, the temperature, the number of cycles, so the speed, over a period of time, there's a buildup of residual stresses, and this causes the material to change from randomly oriented, grain structure to fracture planes. And these planes are called so-called subsurface microcracks, and they develop under the surface and they work themselves up and blow out. And so we end up getting spalling and cracking blown out from inside the bearing and coming up. So it's typically at a depth, in my notes here, of about 0.1 to 0.5 millimeters. So 100 to 500 microns below the surface of the raceway is where we have maximum stress. And interestingly, if a bearing were actually to reach end of life, this would be the failure mode or the damage that we would see in the bearing. And for all intents and purposes, as far as SKF, as soon as any component in the bearing loses some material, it's considered to be failed. Even though the bearing may still be able to rotate and continue in service, technically we would still consider it to have failed. Okay? And what else here now? Actions. So I have on each slide copied in the actions, and you'll see all these in that PDF that we've given you a link for. But how do we mitigate? How do we avoid this subsurface initiated fatigue? Well, first off, we want to make sure we have the right bearing, because we know it's related to load, speed, etc., misalignment, mounting, and so on and so forth. But getting the right bearing for the application and the conditions is key. Use good quality bearings, of course, ensuring you have as clean steel as possible, quality components, and sized, matched rolling elements, etc., so that we have a nicely distributed stress in the bearing, and make sure adjacent components are well designed. Interestingly, I know of a customer that wanted a super precision bearing because it sounded great, like it was great quality. Well, we asked the customer, is your shaft super precision? Is it manufactured to, high precision class? So because, if your mating components are not equivalent or higher in precision than the bearing you're using, you will not get the full benefit, of the performance of the bearing. Okay. So some pictures, and these are in that CAN book. As I mentioned, identifying the damage is, a large part of the activity of performing failure analysis. So getting yourself trained, to see the damage in its different forms, different bearings, different applications, is very important. So I'm not telling you that after this talk you're going to be a bearing damage or failure analysis expert, but you'll be well on your way at least. Okay, so you need to see and touch a lot of bearings from different kinds of applications to hone the skill of doing a great, good failure analysis on a bearing. So you see here some different bearing types. Okay, surface initiated fatigue, and it's sometimes the art will see, initially you'd think, what's the difference between the two? But they're two very different failure modes, and if you misidentify them, you end up with the wrong corrective actions. Okay, so this damage is related to lubrication proper. Okay, it results from damage when the asperities on the rolling surfaces, the balls or rollers and the raceway hit each other. And we spoke about this before we started the presentation. We end up with uncontrolled brakes, and these particles float around and further reduce the adequacy of the lubrication and lead to more damage. You can see here we have a wear as a result of the particles being entrained in the lubricant and dragged along. So basically, it's a result of a reduced lubrication regime. We end up with surface distress. We call this burnishing or glazing. And we end up with micro cracks or micro spalls that initiate from the surface. And that's the key difference. The subsurface fatigue, it blows out from underneath. This starts on the surface and it spreads around. Okay. I did want to mention quickly that the EP additive, need to pay attention, because depending on the chemistry, the EP additive can become aggressive to the point of accelerating this micro spalling. So we won't talk too much more about it right now, but we can address it in the discussions and the questions later. Oh, let me just kick back, if I may. I lost my pointer here. Give me a sec. Okay, there we go. Just wanted to cover off the actions. So what we want to do is ensure that we have the right lubricant with the right quantity at the right time. Okay, because this damage is lubrication related. We want to improve the surface separation capability of the lubricant. Okay, so lubricant important. If you're using oil, filtering is important. Improve sealing if we're getting any contamination in from outside, and that will help to limit this type of damage. So back to the pictures here, and what we see, a lot of spalling, and note there's wear as well involved, and I'll discuss this further later, but we will see layering, different types of damages on top of one another, interplaying with one another, because, well, imagine when you lose material and you have this material floating in the bearing cavity, there will be wear, and there will be more damage, and it's a cycle that just worsens until catastrophic failure. Here are some more pictures. For example, down here, we had some dents resulting during mounting in a deep groove ball bearing. You can see at ball spacing, and these became areas of stress risers and areas of surface distress. And this will grow and spread all around. At some point, we may not even be able to identify that it was in fact denting, at mounting. But if we catch it early, we have a better chance of determining that. Okay. So we're into wear. So wear is defined as the gradual removal of material from a surface. And right up, we have abrasive wear. So those of you familiar with wear, we could have, two-body abrasion or three-body abrasion when we have foreign contaminants or particles introduced into the cavity. We will see some wear even without the presence of external contamination. Light wear during the running in stage of a rolling bearing, it produces a sort of a haze on the raceway that we call the path pattern. Okay, so that is, let's say, normal, but if it's excessive, then we know there are issues. So most of the time, as I mentioned, real abrasive wear occurs due to inadequate lubrication. We have metal-to-metal contact, or the ingress of solid contaminants. Abrasive wear is typically characterized by a dull surface. The raceways will have a dull aspect to them. There are certain conditions, depending on how hard mineral contaminant is and the size of it, where we end up with what's called polished wear. So you end up with a really mirror-like polished surface in the bearing. And some folks that may not be familiar with what a brand new bearing looks like may think there are no issues and no problems because it's really nice and shiny, when in truth it's actually damaged. It's the honing marks have been worn away, and you have this polished surface. So abrasive wear is a degenerative process because, as I mentioned, the more abrasion there is, the more particulate is loosed, and it just gets worse and worse over time. Particles can wear down, the raceways of the rings, or rolling elements, cage pockets. Just a note about cages, and I have a picture of one down here. Cages are typically the softest component and the most fragile component in a bearing. So we'll often see the most dramatic damage, in a cage, and we will often look at the cage when we're doing failure analysis as an evidence to support the fact that there was, external contamination. And so let's go to some of the pictures or examples of abrasive wear. And we will typically see abrasive wear in industries where there's a lot of particulate, mineral processing, aggregates, cement, where we actually get actual ruts worn into the raceways of the bearings. And in advanced stages, heavy pitting and surface-initiated fatigue, et cetera, et cetera. Early stages, we might just see, paths or tracks like this. So, key, and there is a section in that PDF that we shared the link for that speaks about path patterns. So a large component of doing failure analysis is understanding what a normal bearing in normal conditions with no abnormalities, what it would look like once it's run in service for some time. That is important because, using that as a reference, we can pick out any anomalies or anything that's abnormal and flag it, during our analysis and observation, taking evidence and looking at the bearing parts after there's been a failure. Okay, so abrasive wear here, so more. And it's interesting for me, over the years working and doing failure analysis, as condition monitoring has taken hold, gone are the days, or less so, when we'd get bearing components, shrapnel in a bucket, for analysis. sometimes we get bearings that are so clean, you wonder why they were removed from service because, something was flagged and picked up with vibration monitoring, for example, and, it comes in and it looks great. So it's very interesting, but here are some examples of bearings that are far gone. And, over here on the right, we see, the polished wear here on the bottom right, where an outer ring of a bearing has spun in the housing, and we've ended up with that polished surface, but with this circumferential marking, we know that it actually rotated, and that's not what it should be doing. So that would be flagged as an issue. It says here in the notes, the housing had inadequate fit. Many times ring creep is actually related to rotating loads. So imbalance. So you might see something like this in a high-speed fan, maybe an overhung fan or something where we have a slight imbalance and it's actually dragging, the outer ring of the bearing around. So into adhesive wear. So adhesive wear is also a type of lubrication-related damage, and it occurs between two mating surfaces that are sliding relative to one another. It's characterized by a transfer of material from one surface to another. Okay, it's accompanied by frictional heat, and this heat can actually temper or reharden the mating surfaces. So that is a problem. Okay, so the frictional heat produces local stress concentrations where cracking can initiate or spalling in the contact areas. You can see down here the skid marks from a couple of rollers here on the outer ring of a bearing. Smearing or skidding, as it's also called, galling or scuffing, is not common under normal operating conditions. But where applications are running at high speeds, we are a little more susceptible, and especially high speeds with low loads. So again, high-speed fans are notorious for this because typically the bearings are oversized for the application. They sizing the bearing to the shaft diameter, not to the loading condition. And so we have a lightly loaded bearing. And interestingly, bearings are friction machines. They actually do need friction to operate properly, so that instead of rolling elements sliding, we want them to roll. And so, but too much or not enough friction rather is a problem. Okay, so I have thrown up this little image here, where again, imagine a horizontal shaft loaded down into the ground. So at 6 o'clock here is the most loaded rolling element, let's say, and we have the load coming through the bearing and being distributed roughly 150 degrees. Around here is what we call the load zone. So up here, there'll be a little clearance and no load. So what happens is, as imagine that it's spinning, the inner ring is spinning, the shaft is spinning, and we have these rolling elements coming through this loaded area where they're captured and basically held and controlled. But as they come out of this loaded zone, they kind of freewheel, maybe even significantly slow down. And what happens is, in this area right here is where we have a high likelihood of getting skidding or adhesive wear damage as the balls or rollers catch up and accelerate into the load zone. We can get the scuffing or smearing right here. Okay, so up here you see the asperities of the rolling element and the raceway hitting one another, the temperature spiking so high that they actually weld to one another and pull away. So that's adhesive wear. So some of the damage you might see may look like this. Note the torn, what we call the torn edges here of this taper roller bearing roller, and typically it would be running against the flange here of this cone. And other areas, this is a spherical roller thrust bearing outer ring. Notorious because the rollers are heavy, and in applications where there's a high ramp up or decel, accel and decel, we can get skidding, adhesive wear. So into corrosion. So corrosion is defined as a chemical reaction on metal surfaces. We start off with moisture corrosion. Now, moisture, wow, we work with a lot of industries where there's water sprayed, there's water, in the environment, humidity, with the change of seasons, we can have housings breathing, and we end up with condensation inside a housing. So water is one of those contaminants that we're always working hard to keep out. We're always looking for 200 part per million or less of water in your lubricant. The problem is, for example, with oil, oil does get cloudy when it has a lot of water in it. The problem is that you don't see the change until 1,000 part per million. So by the time you realize you have an issue with water, it's probably too late. Okay. So ineffective sealing arrangements can allow moisture, water, aggressive liquid contaminants to enter the bearing cavity. When the quantity of liquid contaminants exceeds the ability of the lubricant to adequately protect the steel, rust will form on the surfaces. Okay. In the absence of oxygen, this rust, this etching, this corrosion is grayish black in color. And the water is wicked around the rolling elements at a standstill. If this is a horizontal application, never mind. No, gravity will pull the water or these liquids down and pull them around. So you see the damage typically at roller spacing or rolling element spacing. And as the bearing starts to run again, these grayish black areas might get rubbed somewhat and lighten. So sometimes it is a challenge to find or determine that moisture was the initial cause for some of the damage that you'll see, because these spots become areas where spalling and flaking initiate and then spread. And you imagine then you will get abrasive wear and surface initiated fatigue and everything else layered all over that. Okay. So, I'm sorry, my apologies. I've been skipping some of these let's say corrective actions, but mind you, we understand that if contamination is getting in, we got to keep it out. So sealing is important. Okay, a very, let's say, low investment, beefing up your sealing to protect your larger investment, all the way to your production. So as well, use the right lubricant. You may, in your oil, might want to use additives, or have additives that will break up the water. You might circulate it so that you can remove the water. As far as grease, you might want to use a thickener that is, let's say, better in the presence of water, like calcium, as calcium sulfonate. You may want to, sort out the breather arrangement on your housing. Maybe have a desiccant in the breather to avoid what we call the breathing. When with the heat and then cooling, we might pull in humid air that will cause condensation in the housing. We might want to deal with that. So a whole lot of things to think about and look at if moisture corrosion is an issue. Okay, some examples here. Okay, see, note, like I said, it's got a slight waviness to it. Hard to differentiate sometimes if it's just lubricant staining, right? So sometimes your oils or your greases might leave some staining on the steel surfaces. So again, it takes a little bit of a trained eye to discern or determine that it is indeed moisture corrosion. And just for effect, I guess here's a roller with a fingerprint, and a rusty finger sweat has left a corrosion on a rolling element. So this you might find obviously with samples and such that are are not wiped down after they've been handled. But yeah, again, grayish black, and it's moisture corrosion. Okay. Frictional corrosion. So frictional corrosion is a chemical reaction that's activated by micro movements between mating surfaces, or let's say components that are adjacent to one another. And these micro movements lead to oxidation of the surfaces, and they may become visible as a powdery rust, and actually a loss of material from one or both of the mating surfaces. Depends on the type of material and the hardness, etc. Okay, so let's look at this first slide for fretting corrosion. So fretting corrosion, again, occurs when there's relative movement. Could be between the inner ring, the inside of the bearing and the shaft, or the outer ring of the bearing and the housing. So fretting corrosion is usually the result of a fit that is loose. So if we see it in the bore of a bearing where we're supposed to have an interference or a tight fit, we know there could be issues. Maybe the shaft is undersized, or the loading in the bearing is much higher than anticipated, and we have an insufficient fit, an insufficient press fit on the shaft. The relative movement that we get causes the asperities to get worn down. These bits detach, and I put this down here, as you can see. They get ground, just this oscillation under load grinds down the high points of the steel surfaces, and we get an accumulation of bits of iron that oxidize. So it'll present itself with different colors depending on the chemistry. If we end up with Fe2O3, it might be more of a reddish orange color. If we end up with Fe3O4, it will be more black. And I like to liken it to dermatitis, right? But steel dermatitis. The issue with excessive fretting corrosion is that the volume is of this fretting corrosion. These oxides are higher than the steel itself, so we can end up with rings that are unevenly supported, and this will have a detrimental effect on the load distribution in the bearing. But as well, the corroded areas can act as fracture notches. So excessive fretting corrosion is not desirable. Okay. Here are some examples of fretting corrosion. False Brinelling, and I see I'm time-wise I'm pushing it here, so I'm going to speed up a little. False Brinelling is basically where we have vibration that causes the rolling elements to bounce, either in the bearing while it's stationary or rotating. And the let's say the magnitude or how extreme it is dependent on the intensity of the vibration. This can happen when a bearing is sitting in stores or in a standby piece of equipment. So very important to consider your lubrication, because your selection of grease could help, let's say, dampen the vibration. How you store it, by putting damping pads, and how it's transported, etc. And in a ball bearing, you get sphered depressions. You can get really deep ones, as you can see here. In rolling bearings with rollers, you'll have more of a longitudinal depression in the bearing. So try to not to expose the bearing to vibrations. That's the key here. Dampen it somehow if you can. Okay. Here are some examples. And a true Brinell is actually a dent. So a false Brinell means that it was made by this hammering or shot peening type of action, and as such, it's not a true dent. Okay? Electrical erosion, macro or micro craters caused by local melting when the level of a threshold electric current value passes through. So when levels beyond the threshold electrical current value pass through the rolling contacts of a bearing. Okay. So the first one is called excessive current erosion. So when you get current passing through a bearing, so going through one ring, through a rolling element, and through the bearing and out, damage will occur. So at the contact surfaces, it's similar to an electric or arc weld, where we have high current over a very small contact surface. So high current density over a small contact surface. The material's heated up to temperatures that range from tempering to melting levels. And it leads to the appearance of discolored areas, the creation of these craters. Typically in excessive current erosion, we're looking at upwards of a 0.5 millimeter diameter of crater. And you can see how current passing through, we end up welding. And then as the rolling elements continue to move, we're ripping out melted material and creating these craters. And then, the excess material gets worn away over time on the rolling element. But, well imagine that this will get nasty as it continues. Obviously, we'll see this mostly in, equipment where, for example, electric motors, etc., where we have current running in the equipment. And, some of the things we can do is sort out the grounding, maybe use insulated bearings. So there are bearings that are coated with ceramics, or more and more popular, a hybrid bearing that uses a silicon nitride or ceramic rolling element that'll insulate, against this possibility of current running through the bearing. So here are some examples. Note the zigzag currents. So whatever's on the raceway would be matched typically, on the rolling element. And when we see this, we know that we're dealing with excessive current erosion. With lower current intensities, we can end up with very shallow craters that are closely positioned. And we end up with, as you can see here, magnified, lots of tiny, tiny little craters. Magnified, we see that we have very brittle and hard areas up top, and then softer areas below, after the material has been melted and then rehardens. So hard and brittle at top, and then annealed, underneath it. And it's one of my favorite damages, because over time you end up with a washboard pattern that looks like this, and you can feel it very distinctively as it's like a crater, well, not like a crater, but like a little rut, a washboard in the raceway. So how do we deal with it? Again, insulating, dealing with the grounding, making sure we're not running, high voltage cables next to lower voltage, etc., etc. Okay. Here are some examples. Before it gets to that heavy washboarding, you might just see light lines. And again, we'd see this in equipment like electric motors and such, where current is going through. Okay. Let's go to plastic deformation. So this is where we have a permanent deformation, where the yield strength of the material in the bearings being exceeded. And we're dealing with, anything to do with nicks and dents, etc., due to handling, shock loads. All the damages look the same, and that's why they're all let's say, covered by overload deformation. Okay, so this one's also a hard one, but obviously if you see a cage dented like this, likely someone wasn't using the best tools. Maybe a hammer slipped, or a chisel slipped, or a drift slipped as they were mounting the bearing. all of that would fall under overload deformation. So, actions to take to avoid this: use the proper method, the proper tools, follow the work instructions, and here are some more damages that would be considered overload deformation. And here are a few more. Okay. Under plastic deformation, we also have what is called indentations from particles. So solid contaminants can get into the bearing. It could come in via contaminated lubricants. So important to make sure your lube, your greases and oils are stored properly. Make sure when you're plugging in your grease gun that you wipe the grease zerk fitting, for example. We want to make sure we're not pushing contamination into the bearing cavity. But contamination can also come from worn or damaged adjacent components like gears, for example. So when these solid contaminants get in, I mean, the pressures we're talking about are very, very high in the contact, in the load zone, in the contact areas, in the bearing. So high that even a human hair could put a dent into the steel, in the right conditions. So this solid contaminant would be overrolled. We end up with a dent. I liken it to a pothole, and soon enough, where winter is upon us, we will begin to see potholes, and we will begin to understand how the pothole grows. So the material gets pushed up, and these raised edges become areas of higher stress, and the rolling element would hammer away, and you end up with spalling or breakage behind that indent. So here you can see a particle was overrolled, and over time it's broken up, and we've got fatigue and spalling behind it. And we liken it. So this is how we determine, where it initiated, because we get this pattern. We liken it to like a thumbnail or beach waves, and we can figure out, where the initiation point was. So the particle doesn't need to be hard. Even soft particles like paper in a dry end of a paper machine, we've seen some nasty dents from paper particles, as I mentioned, because of the high contact pressures. And when the indent is formed, whether it's soft or hard, if it's soft, you actually have a smoother edging. With a harder particle, it'll be a little sharper. Okay, so lubricant cleanliness, careful mounting, handling, during mounting, making sure we limit the ingress of contamination into the bearing from start to finish is very important. Okay, so here are some examples. See, swarf overrolled, small dents. If we zoom in, we can actually see the denting. And mind you, if we get surface initiated fatigue or subsurface initiated fatigue, where we've got the actual bearing particles itself being overrolled, you can well imagine how this grows and spreads over time. Here again, and notice here the two initiation points and the spalling behind them. Okay. Cracking and fracture. So we're getting towards the end, hopefully here. So cracking is the incomplete separation of material under stress. Cracks initiate, they propagate when the ultimate tensile strength of the material is exceeded. And a fracture is basically a crack that propagated all the way through to complete separation. So we have what's called forced fracture. And this is when the stress concentrations as much exceed the tensile strength of the material. We have local overloading and overstressing. Rough treatment can cause fracture. It's a common cause. When bearings are mounted cold and it's hit with a hammer or a chisel, we might develop, fine cracks in the rings of the bearing that eventually lead to separation and through cracks. So, excessive drive up on a tapered shaft, for example, can result in an inner ring fracture. because of the tensile stresses being exceeded, the limits, and then the bearing's heated when it starts to run. And this is an issue with martensitic hardened rings, not so much with bainite or case hardened. Here are some examples. Fatigue fracture. This is when the fatigue strength of the material is exceeded under cyclic bending. So repeated bending will cause a hairline crack. So, if we have a housing, for example, that isn't supporting the bearing ring adequately, we could end up with a fatigue fracture. If a little piece of the lock nut is broken off during mounting, gets underneath that outer ring, we can end up with a fatigue fracture because that ring will flex around that little piece of metal, and we could end up with a fracture. So we want to make sure that bearing seats and housings are fit and form there are to specifications. We want to make sure housings aren't oval, and et cetera, limiting contaminants in the housing prior to mounting to ensure that we have clean and continuous contact around the bearing ring. Okay. So lots of examples of fatigue cracks here, and we notice cracks, where there's areas of heavy spalling. We see a fatigue fracture as a result. Thermal cracking. This one is an interesting one. When we have some contact between the rings of the bearing and a shoulder on a shaft or an adjacent component, we can get enough frictional heat that we can cause cracks to form. And these cracks are formed at right angles to the shaft. And, there could be creep, let's say, a sliding movement between the bearing side face and a spacer, for example, resulting in smearing. And these cracks will form and can go all the way through and cause a fracture. Okay, and it's funny, this one I see rarely. We just got in a bearing last week, and it happened to have thermal cracks. So I'm planning to keep those as samples because it's rare, but it does happen. Okay, so here, and you'll notice the discoloration indicating high heat. Right. So last couple of slides here. The notion of primary versus secondary damage. So now we're talking about the analysis part of it. We looked at some nice slides, nice pictures, really neat, and we might be prone to think that performing failure analysis is very easy, straightforward. The truth is, cataloging the damage is fairly straightforward, but when it comes to recognizing, each damage in its various forms, like I said, in different bearing types, in different applications, when it comes to unpacking the layers of the damage, trying to get at what the primary cause was. For example, here, impact at mounting was the initial trigger event, led to plastic deformation. That was an area of stress concentration, ended up having surface initiated fatigue with spalling that produced contamination in the bearing cavity, deteriorating the lubricant, causing overheating because there was more friction, ended up having the bearing seize that led to a fracture. So, if we caught this bearing, obviously we would have caught it, say, at the fracture, going all the way back and unpacking what actually happened, that's the challenge, okay, to go all the way back to determine that it was something that happened at mounting. Because if we choose the incorrect trigger, we end up with let's say the wrong corrective actions, and we never end up fixing the issue. So yeah, it's fun, but the first thing we want to do, obviously, is when there's a failure, gather and preserve evidence, collect data, take lubricant samples, take pictures of the environment, mark the positions, what parts of the bearing were inboard, outboard. If it's in pieces, try to mark them before we remove them, bag them, check the bearing seat, preserve as much evidence as possible. And with all that evidence, the bearing components, them proper, are key, to the investigation. And uh, we record the visual observations, and we try to figure out what was the original cause of failure. Okay. Um, for those, if the problem it comes back. If the problem then we know we likely didn't, hit it. We didn't get the true root cause, because if we did, it would be fixed. All right. So failure analysis is simply the bearing failure portion is simply a piece of the bigger root cause failure analysis discussion, the bigger puzzle. For those familiar with RCFA, it's important to address true root cause of a failure and not treat the symptom of the failure. So there are many well-proven methods. I'm not going to go into them. Suffice it to say, we know there are tools that you can use to drill down to a root cause, such as the 5 whys, fault tree analysis, cause and effect, etc., etc. So I think that's pretty much all I had for us today. I went much longer because I had a little stopwatch here. But thank you for your attention and for your time. And maybe we have a few minutes to take some questions.
Sure. Thanks, Devan. Yeah, thank you very much. It was a great presentation. A couple of our attendees, they had to go to a different meeting, so they commented that it was a great presentation. They thank you. So I have some questions in the chat room. The first one comes from Ken and says, of the 1/3 that failed by fatigue, what percentage are from subsurface crack initiation?
That's a good question. I do not know the statistics offhand, but I dare say that surface initiate, so lubricate, because anything related to lubrication, um, we see the most. Okay, so surface initiated fatigue is closely related to lubrication issues. So there's a much larger portion of fatigue related failures that would be classed as surface initiated. Okay, subsurface fatigue, because like I mentioned, if a bearing reaches end of life, that's how it would fail. But when we speak about premature failure, we're talking about something that failed sooner than expected. So, and the main reason for subsurface fatigue would be, overloading. So issues with the housings, maybe with the shaft, etc. So, because in the old days, the steel wasn't as clean, but there's been such an improvement in steel manufacturing and manufacturing of bearings overall that subsurface initiated fatigue is low on the list. We do see it a larger percentage in bearings such as the self-aligning ball bearing, and that's mostly because the rings are so thin that oftentimes customers overdrive when they're mounting tapered bore versions of that bearing. They tend to drive them a little too far. And so, subsurface fatigue is a result of losing clearance in the bearing during operation. Okay, so hopefully that gives a little a little idea.
Good, thanks. I think you answered a little bit the second question, but I'm going to go through that anyway. It says, what are the factors which affect fatigue life of the bearing?
So again, fatigue, and if you think of the word fatigue, we're talking about tiredness, right? So that slide that had the cycle, so I can kick it back up, but the slide, here, just share my screen again. So this slide here. Okay, so when we talk about the factors, okay, so fatigue, so you think about, I always think of a paper clip, right? If you remember when we used to break paper clips by bending them, if you remember, we could accelerate the breakage by flexing it much further. So think of that as being loading, right? So load, the temperature will affect, will contribute to fatigue. The number of cycles, so revolutions. So you notice here, this was 10,063,630. So speed will have an impact on how many cycles within a certain time period. But load has the largest effect. So, insufficient support of the bearing due to form issues with the housing is a large contributor to subsurface initiated fatigue. And then also fits being a little, heavier, maybe the shaft is a bit oversized, that could also contribute to fatigue. So yeah, all of those things together. And then, if we talk about surface initiated fatigue, we spoke about, lubrication. So the right lubricant, right quantity, right time, and the right additives, will help.
Good. And I think the next question is actually related to this slide that you were sharing. It says, please elaborate additive effect on surface initiated fatigue. I think you said the EP additive have some roles there, right?
Yeah. So when we think, so we need to understand, of course, we're not talking about lubrication proper here, but the way extreme pressure additives function is by chemically reacting with the surface of the steel. So there's actually an interaction. So as the temperatures are elevated, well, we know from chemistry that when you put heat, it speeds up the reactions, right? So if we end up with higher temperatures, operating temperatures, that actually accelerates this aggressive chemical reaction that's going on. And if we're not careful, so that's why as far as SKF, we do not recommend EP to be used above 80 degrees C. Okay, so you need to be aware of the type of metals in your bearing. And if you're using, for example, a polyamide cage, there could be a chemical reaction that will soften and destroy the cage. So we need to be aware of chemistry. So the EP weakens and is very aggressive as the temperature goes up. So the desired effect, like we said, is that we want a cleaner break when we have boundary lubrication. We want these tips to break off cleanly, and to do that, the EP weakens the surface of the steel. I guess I repeated myself a few times, but I hope we got to the answer or the explanation.
So the next question is, given the number of lubrication-related failure modes, do you have a feel for how many plants have trained and dedicated lubricators as opposed to operators or any trained doing it? So I think the question goes like, do you see any plant training people for these failure mode analysis or catching these things or no?
Well, let's put it this way. I mean, with our customers, we're conducting training on a regular basis, right? So I can't speak for the customers that don't engage with us, but what I can say is that from experience, certain industries have, let's say, a little more advanced maintenance teams and maintenance strategies in place, and I've put in the systems, monitoring systems. As far as when I say monitoring, I mean, there's one thing, giving a lubrication tech instructions to go out and put a certain amount of a certain grease in the equipment, but how do you get the feedback back into the system to say, yes, this was actually done? You know what I mean? So we see, for example, in oil and gas, more mature programs in place, and other industries may be, let's say, less mature, a little more reactive type of program, of activities going on in there. So I'm not going to name any names or throw anyone under the bus, but certainly as time's going along, with the focus on reliability, let's put it this way, more and more facilities have reliability teams in place, and as a result, training and adequate knowledge and the requirement for that knowledge is increasing. So we are seeing increased requests for training on bearing maintenance, lubrication, and also, like as Behzad mentioned, I was up north last week conducting a bearing damage and failure training as well at an end user. So they're interested, they want to learn, they want to improve, and reliability is the focus.
Okay, good, thanks. Next question is there a minimum amount percentage of fretting that is considered acceptable?
Yes, and the reason is that it is normal to have fretting corrosion around the outer diameter of a bearing in a loose fit application. Okay, so we mentioned this is the result of oscillation. So what happens is when the bearing's under load, it gets squished and it grows. So part of the reason for the fretting corrosion on an outer ring that is stationary is not because the outer ring is creeping, but because the outer ring is growing as a result of being compressed under load, and it's actually doing this cyclically. So you will have fretting corrosion underneath. How much is too much? It's hard to say. It's more from experience. I would say any fretting corrosion in the bore or the outer diameter where there's supposed to be a tight fit would be suspect. We would flag it. Okay. Excessive fretting corrosion would look something like this. It actually has some thickness to it and some texture to it. So it's hard to express, but it's more from experience that we we determine that it's excessive or not bad. But either way, we would, even if it's normal, if we expect it to be there, we still flag it, and we still say, Mr. Customer, Mrs. Customer, Ms. Customer, please confirm that your housing is to spec, your shaft, like I said, unless it's a loose fit, I don't want to see any markings like this in the bore of the bearing. Certainly.
Okay, good, thanks. The next question is, at one time, the corrosion inhibitor in new bearings was reportedly not compatible with polyurea grease. Is this still the case?
Good question. I do not believe that is the case anymore, but we do still, recommend. I believe we obviously use a third-party product for corrosion as a corrosion inhibitor, and I would still, prefer to have a compatibility test if there's an issue. Mind you, as part of the installation process, there is a recommendation, to wipe off, with a lint-free rag, as much as possible, the bearing without introducing contamination into it. But one way to deal with that is to just flush it. You flush it out. Certainly, spray some solvent and clean it as best you can if there's any concerns. But worst case, because certainly larger bearings have a lot more corrosion inhibitor to the point where it's dripping off the bearing. And in that case, it might be necessary to confirm compatibility. But as far as I know, and I don't hold me to it, I don't know that there is an issue. I haven't of late run into any situations where customers being concerned. I mean, we have a diarrhea grease in our short list of lubricants, and we've never had any discussions around compatibility with our current rust inhibitor or corrosion inhibitor. But we can. I believe it's a Fuchs product that we're using right now, but I'm not certain if different factories are using different different rust inhibitors. To be honest with you, but good question though.
Good. So is this bearing failure analysis services free by SKF, or you charge for that?
It's a charged service. It's a value-added service, and we usually, take it case by case. But if anyone is interested in availing themselves of the service, please contact your SKF authorized distributor, or if you have contact with an SKF account manager, inquire, and certainly, a quote or budgetary could be provided for you. I will not say that there are not situations sometimes where an analysis is performed free of cost, but that's more the exception, than the rule. So we have, part numbers for certain sizes. We go say 0 to 4 inch, 4 inch to 12 inch, and just to cover the cut, because it is typically an engineer engineer doing the work, signing off on it, and we produce a formal report. So just to cover off that activity, as you would expect for yourself to be compensated for your time, we certainly would. And as I would say, when we're doing a bearing failure analysis, I'll be honest, it's not because of the quality. It's not a quality issue most of the time. Okay, so most of the time it is some deficiency in the facility, in the machine, like we said, largely lubrication related, contamination, etc. So our customers are coming to us, and I'll be honest, it's not only SKF bearings that are analyzed. Bearing is a bearing, let's say, and they want to know how they can stop this failure from happening again, from recurring. So they value that, and as a result, they're more than willing to pay, right, for that service. So
okay. So can you go back to the slide that you had about the subsurface fatigue, that you show that 630 million revolution? And there is a question here by John, or you passed it.
yeah.
He did a calculation that 630 million revolution, if that's 3600 RPM, is equal to 122 days of operation. And he says that that's not a very long time at all. Do you think that 630 million revolution is a typical time for this change to happen? Then how long until a crack below the surface develops after that?
Okay, great question. So let's put this into perspective. This was performed in a laboratory. So the laboratory has, and I don't know if it's easy for you to read here. This is what it says, Behzad. It says changes in structure beneath the raceway surface over time, in brackets, highly stressed, well lubricated, small, deep groove ball bearing. So I would say ignore the revolutions. All the reason why the number of revolutions was put here was just to give a sense of, you know what I mean, the progression. But typically this type of bearing would not be heavily loaded. There's that, first of all. Okay, so this was a deep groove ball bearing with a heavy, unnaturally heavy load, because the lab cannot wait years to get results, right? So this is a case where it's artificial conditions, and they are forcing, let's put it that way, the damage to occur in a time that they can pick it up, and likely they probably were running at a much higher speed, Behzad, because they're not going to wait 122 days to be able to cut bearings and see the change in the microstructure of the steel. So
so it's highly stressed, higher speed than 3600 in the lab, so they can get the result as soon as possible.
Accelerate, yes, because it's to recreate, a real world problem, but any testing, we want to do it in a short time as possible. So they have special equipment, right, in a lab that will simulate, but contracted as far as time.
Yeah.
So just use the millions of revolutions here as a gauge of, you know what I mean? What's the word? Progression, right? Rather than hard time.
Okay. And the last question that I have, I don't know if you can answer that or not, but it says, Yusuf says, thanks for useful information. Based on what Besha discussed, how can choose for synthetic base oil versus mineral, especially in food grade machines? Do you want to comment on that?
Repeat that again, Pesat.
I think the question is for the food grade application, for the food grade bearings in the food plants, how we can choose synthetic base oil versus mineral base oil for the grease.
Okay. Now, Behzad, I'm not purporting to be a lubricant specialist, but you and I both know that, for food grade greases, for example, is using white mineral oil, right? And it's more a function of the chemistry of it, right? Is it safe? Is it safe? So we do know that synthetic, so, lubricants that are developed in the lab may have enhanced performance, right? Now, I don't know, Bersad, you might know better.
Yeah, we have, well, I shouldn't talk about Petro-Canada lubricant products because it's not a sales talk, but there are synthetic base oil available in the market which are suitable for the food grade applications. Yes. So I think a lot of lubricant companies, they have that, and they look at it based on the pull point and the application of the grease and the bearing or the system. So Yusuf and I, we can talk about that later, so I don't want to take a lot of time here. So I don't have any more questions here. Is there any question in the audience that somebody wants to raise the hand and ask?
And thank you everyone for hanging on here. I see
yeah. Well, I want to say that you had a great presentation because we are almost 30 minutes over and almost everybody stayed. So it means that you did a great presentation. Thank you very much for that. Before we leave, 3 things that I want to remind everybody. Number 1, this presentation has been recorded, so I will upload it into the STLE Toronto section YouTube channel, and I will send the link out to everybody to look at it. Then I'll also add the PDF link into that email. Next webinar is on October 11th about the EP properties and base oil viscosity of the greases for the rolling bearings. And the last item is, just for your information, Toronto STLE won the Best Section Award of 2022. I just want to thank all the executive members on the call here and off the call for all the support that they gave to the section within 2021 and 2022. And by that, Devan, if you have anything to add, please do so. Otherwise, we can end this webinar.
Thank you for your time and your attention. I'm just putting, something in the chat there. Thank you for the opportunity, and I always enjoy the sessions that we have with the chapter. And yeah, take care and have a lovely day.
Thank you, Devan. You too.
Bye bye, everyone.
Thank you. Bye, everybody.